In this video, we are going to talk about factor analysis. And as our example data set, we're going to use the Chow data. This is a data set that we have matched with propensity analysis. And now we're going to explore some of the information. The correlations, particularly between some of the values at baseline. So at baseline, the values that were collected were spherical equivalent. We've computed this from sphere and cylinder. KT, keratometry, computed from the average of KT horizontal and vertical. Eccentricity, the horizontal visible iris diameter, pupil size, central corneal thickness, and other variables that we're going to look at are axial length at baseline and axial length at 5 years. Now the first thing we want to do is create a correlation table. And we want to correlate these variables, so let's go analyze, correlate, bivariate. We have E value, HBID, CCT, KT. Let's also add in here baseline axial length and 5-year axial length. Now these first set of values are all baseline values, axial length. This is axial length after 5 years. We don't have these values at 5 years, just at baseline. So let's see what we have. And we look here, and for example, if we come down to axial length at 5 years, we notice that all variables are significant. And if we look up through this table, we see, for example, pupil size is also correlated to HBID, central corneal thickness, KT. And KT is correlated, of course, to E value, HBID, pupil size. They're all correlated with each other. Now, let's do a regression analysis. Regression, linear. We want to do multiple regression. We're going to look at axial length at 5 years as a function of E value, HBID, pupil size, central corneal thickness, and keratometry. So we're going to see which one of these variables is significantly associated with axial length 5. So we run it, and we've accounted for 32% of the variance, and that's significant. Overall, the model is significant. But when we look at the individual values, we only see that HBID and KT are significant. All the other ones are not significant. Now wait a minute, we just said that in our correlation, everybody was significantly related to axial length 5. And here we're saying, well, not so fast. Only HBID and KT are significantly associated. So this is the fundamental problem of multicollinearity. All these values are related to each other. So when you look at eval, eccentricity basically, you are controlling for HBID, pupil size, central corneal thickness, keratometry. When you look at HBID, you're controlling for E value, pupil size. And so basically when you're looking at each of these values, you're controlling for all the others. And so if they're correlated, they steal variance from each other. And so in a worst case scenario, nothing would be significant because they all were so correlated that they stole all the variance. But in this case, they're stealing most of the variance and just letting a few variables come through. So what do we do with this? Well, one thing we can do is our dimension. We have basically 1, 2, 3, 4, 5 measures of the same thing. And so we want to reduce this dimensionality. And so how do we do this? Well, we use factor analysis. And factor analysis is a method of saying, okay, there is some underlying latent variable that we cannot observe that is basically driving all these other measures. There could be one factor, there could be multiple factors, and that's one of the questions we ask. How many unique factors are there? So to do this, we're going to go into dimension reduction. There's only one option here, factor. And we're going to add our variables in here. Notice we don't put in AL5 here because we're just looking at the independent variables and the inner correlations between those. And when we start, we're going to use principal components analysis, because what principal components analysis does is look for the most efficient mathematical reduction. Now, it could come out with several dimensions or not, but our main purpose of principal components is just to look to see how many factors we have. And we're going to have the computer select all factors with an eigenvalue greater than 1. Now, what's an eigenvalue? An eigenvalue is the variance of the latent factor. We'll see this a little more in a minute. Another thing we want to continue. Another thing we always want to remember to do is in options, click on this sorted by size. It just makes the interpretation a little easier. We'll see what that looks like in a second. So let's go ahead and do this. Oh, and another thing, let's look at a scree plot. A scree plot, well, we'll see what it is. Okay, this is a scree plot, and it looks at eigenvalue here by number of factors. So there are 5 variables, there's 5 possible eigenvalues. Now, we had chosen to only consider eigenvalues greater than 1. So there is a possibility of a total variance of 5. Each variable represents, so if you think of standard scores, each variable has a mean of 0 and a standard deviation of 1, or a variance of 1. And so that gives us a possibility of having 5 factors. And each of the variables contributing a 1 unit of variance, so 5 variables, 5 factors, a unit potentially of 5, a variance of 5. Now, we notice that the first factor has a variance, the eigenvalue is 2.491. That's like the variance accounted for by this one factor. All the rest of them are less than 1, and so we look at this, and 2.491 divided by 5 is the percent of variance is almost 50%. So we've accounted for these 5 variables share about 50% of the variance. Now, why are we just looking at factors greater than 1 when we actually have 5 factors listed here? Well, an eigenvalue of 1 is an individual question. It has a variance of 1. So if a factor is accounting for less variance than 1, it's not even accounting for the amount of variance in one question. So it doesn't really do us any good to have an eigenvalue that's less than or equal to 1. So in this case, these 5 variables, E-value, HVID, pupil size, central corneal thickness, and keratometry, all add up to 2.491 eigenvalues, 50% of the variance is shared. Now this little thing that's right here, these communalities, this is if you did a total score, like you had a multiple correlation of everybody, the correlation of E value with everybody else is 0.219. Correlation of HVID with everyone else is 0.6, and so forth. So we see pupil size has the greatest correlation of when you combine all the other variables. E value has the lowest. We come here and we talk about a component matrix. These are basically also sometimes called factor loadings. And we sorted them by size. So pupil size, as we noted up here, pupil size is most correlated with all the others. And so it comes out first. It wins. And basically what this factor is an unobservable underlying dimension that is made up or measured by these 5 measures. And so pupil size is correlated with that hypothetical factor at 0.867. The HVID at 775, and the lowest correlation is E value minus 0.468. Now notice some of these are plus and some of them are minus, and basically what this means is the factor score is going to reflect a common direction, but 3 of them are positive, so that the overall factor is in a plus direction with pupil size. A plus direction, it gets greater with as HVID increases, it gets greater as CCT increases, but it decreases as KT decreases and E value decreases. So, and it's not necessary for the negatives to be at the bottom. A minus 0.657 is as strong as, or identical in strength related to the factor as a plus 0.657. In this case, it just happened that the 2 negatives are on the bottom. All right. So again, the scree plot just plots out the individual ones, and it's related to this table, 2.491, 0.875. It's just a graphical observation with 1 being the cutoff. And we see here that we really only have 1 factor. In our study, our baseline variables, these variables that we measure are all correlated with each other. And so we can reduce the dimensionality of our study from 5 variables to 1. And we're going to do that in a minute. One of the things we want to do now is run our factor analysis again. We have determined that there is one eigenvalue, 1 factor that we care about. So let's go to dimension reduction factor. And in descriptives, really nothing that we really care about for now. Extraction. Now, we had chosen the method of principal components. That's this mathematical reduction. A lot of people like to give names to factors. In our case, there's only 1. It matters a little bit less. But there's really the 2 main types are principal components and principal axis factoring. Now the difference is that principal component is basically using all the variability of all the questions. Principal axis factoring goes about finding the best fitting underlying factor or dimension but it acknowledges that questions have their own unique variants that aren't related at all to the factor. So we look at we are going to do this looking at the adding in this component. So we get a really unique value of, or a cleaner value of the underlying factor. We have, before we based it, picking things out, now we're going to say, okay, I believe there's one. We're just going to do one factor. We do that because we want to save our factors, or we want to create a new variable, and that's going to be a factor. We're going to get for each person a factor score, and we're going to use the Anderson-Rubin transformation. And I like that because that means that the factors all have a mean of 0 and a standard deviation of 1. And we'll display the scoring coefficient. Now, in this case, there's only one factor, so things are a little simpler. If we had more than one, we would do this rotation, which then finds a balanced, it balances the variance among the different factors. Usually there's a winner, a big winner, and then it rank orders down. This rotation just basically balances the variance across factors, makes them a little bit more interpretable. So we're going to calculate scores. We have our options by order, and let's see what this gives us. Now, one thing I want to point out, total variance explained. If you'll recall, before we had 49% of the variance explained. Now we have 40%. Why did it go down? Well, because we have eliminated from the factor that unique variance. So we've accounted for less variance between the variables, but the factor is a more pure measure of this underlying factor. Our discrete plot's the same. Our factor matrix, we see that pupil size is the main size, and it's a positive. Notice, let's compare that to, it's 0.9. Up here it was 0.867. So it's a little bit more related. 0.691 is HVID. 0.775. So you can see that the correlation with the underlying variable is tighter because we've picked this principal factor analysis, axis factor analysis, instead of just finding the mathematical reduction. The other thing to notice here is that we have added a variable. Now, actually, I had that save on for the first one. I don't want that one. This is the factor score. This variable is a new factor, is a new variable, and it's a score based on the based on these 5 variables as they're combined. And if we do a descriptive on that, we're going to see that we have a mean of 0 and a standard deviation of 1. That's the Anderson-Rubin. Now, what we can do, and what I like to do to bring the scale back to something meaningful, because this is now a scale where it goes from -3 to +2.5. And in terms of the factor and I characteristics, what does that mean necessarily? Well, the scales are all different for our questions, but the one that is most significant is pupil size. So what I would do is I would go into Analyze, Descriptives, and I would look at pupil size. And I find that the mean is 5.65 with a standard deviation of 6.4. So if we were to go and multiply our if we were to go through and multiply our factor score, our factor loading for each person by the mean or by the standard deviation, multiply this number times the standard deviation and add the mean, we would put our factor scale, our factor score, in the context of pupil size. I mean, all these scores are similar. I just took the heaviest, I would take the heaviest loading from the dimension. But you might rather do e-value or KT or HVID, whatever, it doesn't matter. It would put it in the scale of these. And so if we do a correlation, let's do a correlation. Let's look at the graph of let's do our factor score, and let's do pupil size. We can set our markers by lens type 2, just for the heck of it. So, well, it'll come out labeled. So what this graph shows us is that the pupil size, as the factor score increases, pupil size increases. And it's a little hard to tell from this graph, but basically the greens have bigger pupil size, and they're from the spheric growth model. That is, there were two types of lenses, aspheric and spherical, and we won't worry about what these mean right at the moment, but the spheric, the greens, they were growing. They didn't have good myopic control, and they had the biggest pupil sizes. A controversial point, to be sure. Not many people believe that's true, but that's our data. All right. So here we have shown looking at a particular thing. We can also, let's look at let's do a graph, another graph, a box plot. And let's look at factor score by lens type 2. And so we see that the highest factor score of those 5 variables is in the group that did not have good myopic control. And the lowest factor score is for those that had a spherical lens and had no growth, and aspheric is in the middle. Now, this is a propensity matched sample, so aspheric always falls in the middle by definition because we balanced all the parameters on aspheric and spheric, so it's going to show up in the middle just because that's the nature of how we matched them at baseline. But when we look at the relationship of baseline variables and spheric, that balance that does not alter the fact that some of the baseline variables are related to growth, whether it's spherical or lens. We can't necessarily, we wouldn't want to put them together, but we can do that. In fact, let's take a look at that. Let's do a graph, scatter, and rather than pupil size there, let's put in AL5. So this is the factor score at the baseline, 5 variables put into one factor. And this is 5-year growth. And lens type 2 are those 3 types. Really, there were 2 types of lens, aspheric and spheric. And then we split that one into 2 groups, one where there was no myopic control and one where there was. And let's look at that. And we can see here that as the factor score increases, axial length increases after 5 years. We can add regression lines to that. And we get, we're accounting for 16.553%. So our aspheric, the factor score, it's a little flat. That's the blue line. It's flatter. It has a correlation of 0.16, r squared of 0.16. Spherical no growth, also 0.16 r squared. But for those eyes that grew and had spherical lens, there was a pretty good relationship, accounting for 55% of the variance in axial length at 5 years with factor score. Now, one of the things that we are kind of a little bit concerned about is that let's do a graph, scatter plot, and let's look at baseline axial length. And we see here why we divided into the spherical group into 2 groups. The blue and the red are an aspheric lens and a spherical lens that really didn't grow too much. That's the red. But then there were these other people that grew a whole lot, and we defined these. I mean, there was nothing that said there's nothing that said these groups were going to do this. We did it post hoc. We looked at the relationship of aspheric baseline and axial length 5. We drew confidence intervals around that, or 2 standard deviations away around it. And then if you fell outside 2 standard deviations from aspheric, then the spherical group was defined as no growth if they stayed within 2 standard deviation, and growth if they went outside. And now we're asking, is there some way we can account for this difference? So we were looking at the baseline variables. Now, when we look at our graph up here, we're not adjusting for baseline axial length. So this is a noisy graph due to the fact that people can be anywhere along here at different levels of axial length. So what we'd kind of like to do is adjust this figure so that we are looking at axial length 5 adjusted for baseline variables. Now, one way we can do this, we can ask the question in a multiple regression where we have axial length at 5 years as a function of baseline axial length and the factor score. But we want to do a scatter plot and look at the data. We don't have a way of doing 3 dimensions in SPSS, so we're going to cheat a little bit. So what we're going to do is we're going to analyze regression linear. We have AL5. We have AL5, and baseline. And then we're going to save unstandardized residuals. So basically what we're doing when we save the residuals is we're taking out the model. We're removing this line, and we're just going to have scattered points around that line, and then we're going to see if that residual can be explained by the factor. So let's do that and see what we've got. So we do that and we come to our table again, and we see that we've added this new variable residual, and these are all the differences from when we have a regression line in here, the difference between each of the points and the regression line. So we have this new data, and it's just residuals, and we have removed axial length at baseline. We've removed the variance due to axial length at baseline. And now what we want to do is plot these two. Now, one thing I should note is that we have no meaningful scale. These are both been standardized to means of 0 and a standard deviation of 1. Let's look at analyze descriptive residuals. Well, it's not a standard deviation of 1, but it is a mean of 0. And we could do the same thing we did with the factor score, and on this case, though, we could compute the axial length at baseline, the mean and standard deviation, and we can multiply the residual, each individual residual, times this times the standard deviation, and add the mean, and readjust those residuals from a scale that goes from -1 to +2 to a score that goes from 22 to 28 and has more meaning in terms of baseline axial length. Although actually that's not really relevant here because we're not looking at, we've removed baseline from our scale. So anyway, so graph, legacy, scatter, define. All right, now instead of AL0, we want our factor score, and we want our factor score to predict the residual. Because remember, the residual is the variability that's left over after we've taken out the initial axial length. So we want to see, can we still account for some variability after we have removed this baseline, which was so correlated with the follow-up here. Let's see what we get. And why, yes, we can. As the factor, those 5 variables, the simple summary of those 5 variables, as that goes up, then we've accounted for our residual. And the interesting thing about this is, like we kind of said before, the correlation, you can see how much more variability, how much steeper this green line is, which is the spherical no growth group, or spherical growth rather, that when myopia is not controlled, the adjusted axial length at 5 years goes way up. So what this means is for low factor scores, you're going to have less growth. For higher factor scores, when those values are higher, then you have more axial length growth. The red is the spheric no growth, and really the red, the spheric no growth and the aspheric groups are not as related. They're still kind of related, but not as related as the spheric growth. And you can see here our R-squareds are pretty high. So the spheric growth is 0.543, and it was somewhere in that neighborhood before. Spheric growth 0.55. But aspheric and spheric were a lot lower. When you take out the baseline axial length, they actually become a little bit more related, or show this that these factors are also important for them. It's just not as dramatic. So if we go back and look at our factors, we see that these are positive correlations, meaning pupil size increases. Let's go to the pupil size is related. It has a correlation of 0.9 with the factor. And as pupil size gets bigger, there's more 5-year growth. As HPID gets bigger, there's more 5-year growth. As CCT, central corneal thickness, gets greater, thicker, there's more growth. As KT becomes more powerful, there's less growth. As eccentricity becomes more eccentric, elliptical, there's less growth. So these things combined together to give us that final score. And you can think about what it means. Why would those things all work like that? And what do they do with light inside the eye, maybe from the periphery or whatever? How might that impact myopia? And so you can kind of use these data to explain the eye characteristics that at baseline, they actually do a pretty good job of predicting growth over 5 years. And that's it.